Welcome back. To derive the probability of default under Merton's model, we need some extra probabilistic assumptions on the behavior of the process Vt. As Black-Scholes do for the price of the underlying security, Merton assumes that the value of the company under evaluation follows a geometric Brownian motion. On screen, you can see the stochastic differential representation of a geometric Brownian motion. The quantities involved are Vt, obviously, but also mu v, sigma v, and Wt. Mu v represents the percent drift of assets, that is why it is multiplied by Vt, and tells us if assets have some deterministic growth trend. Sigma v is the percent volatility of the assets. It is a measure of their riskiness. Finally, Wt is a standard Brownian motion.
Now, if you are not familiar with the Brownian motion, it is sufficient to know that the Brownian motion is one of the most important stochastic processes in probability theory. From a heuristical point of view, a stochastic process can be seen as a sequence of random variables indexed by time. And in the particular case of a Brownian motion, these random variables are normally distributed under the assumption that we can represent them in this way, where we have standard normal z with mean 0 and variance or standard deviation 1 times the square root of dt, where dt is an infinitesimal time step. This construction tells us that the dwt you see in the slides is essentially a normally distributed random variable with mean 0 and variance dt.
Solving the stochastic differential, we discovered that T is a log normally distributed random variable. In fact, it is the exponential of a normal, represented by T. Notice that all the other quantities are just deterministic amounts, nothing more than numbers. On the course platform, I am uploading my lecture notes in stochastic calculus. They go beyond the scope of the course, but if you are interested, you can find a lot of useful extra information and proofs.
So, if you have a look at the formula here, you see that the logarithm of T follows a normal distribution with a given mean and a given variance that you see in the formula. Now, how can we use this information to compute the probability of default of our counterparty? Now, the probability of default of our counterparty is the probability of the event T being smaller than equal to B, the liability level. Okay, we can then exploit the relationship between the logarithm of Vt and Vt. We know that the logarithm of Vt follows a normal distribution. This implies that Vt follows a log normal distribution.
And here it is, the probability of T being smaller than equal to B corresponds to the probability of the same relationship in the logs that we can express in terms of phi, the cumulative distribution function of a normal distribution.
Have a look at the probability of default according to Merton's model. Now, this probability increases in the liability level B, and this totally makes sense. It decreases in V0 and mu v, that are two measures of the financial solidity of our counterparty, of the company we are considering. And again, it increases in sigma v, which is a measure of the volatility of the asset value of the company. So I would say not bad for a toy model.
Now, we may also be interested in evaluating the company assets, including equity and debt, at any time t before T. Default can only happen in T, but the assets of the company do vary over time. We know that ST and BT are related to an EU call and an EU put, respectively. Their values in T will be nothing more than the discounted values in T of the corresponding payoffs. This is Black-Scholes-Merton theorem in disguise. In order to evaluate the quantities we are interested in, we assume that there exists a deterministic risk-free rate on the market. In the following formulas, R will substitute mu V, and this is in practice the difference between risk-neutral and market pricing. Okay, not really rigorous, but you get the idea. But you will find more details on the platform. Black-Scholes-Merton theorem tells us that, in perfect and complete markets, the fair value of an asset in T is simply the discounted expected value of the asset at maturity, conditionally on the available information. This comes from the fact that we are playing with martingales, and the quantity Ft that you see on your screen is the so-called filtration. That is the collection of sigma algebras, the information, more prosaically, generated by the asset process Vt. As for H, it is a generic functional. Okay, then for equities we obtain the standard Black-Scholes formula for a European call. The only difference is that the underlying security are the company's assets and the strike price is capital B. Similarly for debt, where we also need to discount the liability level capital B and then plug in the value in T of a European put on VT.
Okay, that's all for this video lesson. On the course platform you can find a lot of additional material related to the mathematical computations involved by Merton's model, and most of all you will find interesting relationships we can derive among the different quantities of interest for credit risk, from the PD to the recovery risk and the loss given default, under Merton's model.
Once again, thanks for your attention and goodbye. Hey, don't forget the course forum. Ciao ciao!